Bismillahirrahmanirrahim. Hello, everybody. Today we will talk about a very important topic. It is called vibration isolation. How to isolate the vibration from your machine, from your instruments. And we can find the same title or the same topic under another title, which is transmissibility. Transmissibility. Also, you can find it under the title response to harmonic or response to base excitation. Right? Base excitation. This is very useful when you are designing a suspension system. So we can model the problem as following. You have a mass, something like that, and this mass is supported to a ground, but in our case, the ground itself is moving. So there is a motion to the ground. So here we have an xg. xg is the motion of the ground. It is a function of time, and uh, we can model it in a harmonic function like x capital G sine omega. We will use omega bar t. So the omega is the circular frequency of the ground. So the ground is moving by a sinusoidal motion. So if you fix your mass to the ground directly with a fixed support, so the same motion of the ground will be transferred to the mass. However, we usually use a suspension system, something like that, K, and the damper, C, and K is the spring stiffness or the spring constant. So by this, you isolate the motion of the mass from the motion of the earth. So now we can name it as only x. So x is the motion of the mass and the xg is the motion of the ground. Now we want to prove that x of the mass is less than x of the ground. Otherwise, you are designing a wrong suspension system. This is the suspension, which consists of spring constant and spring damping. Okay, so now we want to write the equation of motion. What will be the equation of motion? Equation of motion of this system. Okay, as we know from our basic study of vibration, if you have a mass like this, if you have a mass like this one, and the mass is supported to the ground by a stiffener K and a damper C, and the ground is fixed, so it is not moving. So you have only one motion, X, of this mass. By a simple analysis, we can write the equation of motion to be like that. It's very famous in vibration or any dynamics, that mx double dot زائد cx dot زائد kx equal the applied force. So this is, we call it a dynamic equilibrium between the external force, which is F of t, and the internal forces, which is inertia forces and damping forces and stiffness forces. This is the equation of equilibrium. Okay. So in the very famous case, when F of t equal F capital, which is the amplitude of the force, sine omega bar t, we know that the response of the system will consist of a homogeneous solution and a particular solution. Usually we are interested in the particular solution, which is the steady state solution, because the homogeneous solution will dissipate by time because you have a damper C, so it will dissipate. Because this is not because you have a damper. Usually the transient solution, which depends on the dynamics of the system, dissipate in the very few first moments, and the particular solution, which depend on the external force, will sustain as long as the force is applied. So the response in general, x of t, will consist of two parts, x homogeneous, and this is a function of time, that x particular, also function of time. So this one will diminish by the time, and the most important one is x particular, that we know that it will be f capital, okay, divided by k. K is the spring stiffness, and this part we call it the static deflection. So this is the static deflection, or this is the deflection by which the system will be deformed if this F is applied statically by this amplitude only, without this harmonic, without the omega bar. But because of this harmonic, or the dynamic identity of the external force, this will be multiplied by a dynamic magnification factor that is 1 minus beta square all square plus 2 zeta beta all square. And we know beta, this is the frequency ratio. This is the ratio between the external frequency that you apply by your force, okay, and the internal frequency of the system, which is omega n. And we know that omega n is root k of the system by the mass of the system. This is the natural frequency of the system by which the system will vibrate if it is vibrate without any external force. So this is the free vibration frequency, or we call it the natural frequency. And zeta, this is the damping ratio, which is the C, the damping coefficient of the damper, by over C critical. This is the critical damping, and we know that critical damping is 2m omega n, and omega n is defined here, which is root k by n. So this is the amplitude of particular solution. We miss some part, which is time. How to write it? We can cut this part like this. Sorry. Okay, I move it somewhere else. Okay, front page. Okay, let's move it here. Okay. Okay, again, so sine omega bar t minus phi. So this is the amplitude of the motion. F by k, this is the static deflection, divided by root 1 minus beta square all square 2 zeta beta all square, okay? Sine omega bar t, so the response of the system will isolate with the same dynamic, with the same harmonic of the applied external force, which is sine omega bar t, but shifted by phi. What is phi? Phi is 10 inverse 2 zeta beta over 1 minus beta squared. This is what we have designed, or what we have studied in any simple vibration course, okay? So this part is just a revision that will help us proceed in our analysis, okay? So let's go back to our analysis. Now, we want to find the equation of motion. The equation of motion is simply like that. Also, it is mx double dot, but now this x, this is the motion, so mx double dot plus cx dot, but now the relative motion between this mass and the ground should be considered, because the force that will be generated in this damper will result from the relative motion between its two edges, this point and this point. So this point is moving by x and the other point is moving by xg. So it should be x minus xg dot. Okay. So this is the relative velocity between the two parts of the damper or the dashboard. Similarly, the first term will be x minus x. This is the relative motion, or this is the difference between the motion of between these 2 points. Okay, equal what is the external force? There is no external force, so equal 0. So we can rearrange this equation to be like that: mx dot the cx dot plus kx equal. Let's move this part to the right, part, right hand side. Okay, so it will be kxg plus tx dot g. Okay, I think it's so simple. So given that xg is like that, we can rewrite our equation to be mx dot dots cx dot that kx equal. Okay, so it will be kxg is xg capital. This is the amplitude of the motion of the Earth. Okay, sine omega bar t plus c, and this is x dots. So we have to differentiate this part. It will be xg, and due to the differentiation, omega bar will come here, omega bar, and sine will be cosine after differentiation. So c x bar xg omega bar cosine omega bar t. Okay. So now, as you can notice, that we have two harmonic forces because x times x, k times x is the force, okay? But it is a harmonic force. C times x times omega bar, okay? This is the units of also force. This is the stiffness force, and this is the damping force, okay? But both of them have the same harmonic, so we can add them the same way we're adding harmonics, okay? So if we have a reference here, if we take this as a reference, this line and that line, okay? Let's model it by vectors. Make this color. If the length of this vector is kg, sorry, kxg, kxg. So it represents the amplitude of the first force. And this angle is omega bar t. So what is kxg sine omega bar t? It is the vertical projection of this vector or of this force, okay, on the vertical line, okay, the vertical axis. Okay. And the second force is cxg omega bar cosine omega bar t. So it is sine, this one is cosine. So to represent it on the same graph, the cosine force should be normal to the sine force. So we can draw it here with the same angle omega bar t, or simply we can make it normal to the first one. Okay, something like that. Okay, and this is the right angle. This is the right angle. Okay, this is what to write here. The length of this vector will be c xg omega bar. Okay, so this is the applied two forces. Okay, this is equivalent to what? Equivalent to the external force in the simple mechanical vibration. This is the right hand side vector or side force. Okay, so the resultant of these two harmonics, we can replace them by a single one. Okay, it's draw the diagonal of this triangle. The diagonal of this triangle, I'll call it F. Okay, this is the magnitude of the resultant of these two forces. And what will be the magnitude F? What is the value of this F? F will be the root of K xg all square plus C xg omega bar all square. We can take xg as a common factor and it is squared, so we can extract it outside the root. So it will be K, sorry, I'm sorry, so that, so xg outside this part. So now I can write K squared plus C omega bar all square. Okay, let's take this term and analyze it. Square root of K square plus C omega bar square. If we divide this part by multiply by K, okay, and divide by K, okay, and divide by K, and K I'll put it inside the root, so it will be K square. This is K square. Okay. So now this is equal K root 1 plus C omega bar over K all square. C omega bar over K all square without this square, we can write it C from this definition. Okay, C is equal to zeta times C critical. So this is zeta, and this is C critical, omega bar over K. C critical equal to M omega N. So zeta times 2M omega N, omega bar over K. So I can move this M to the denominator of K. So equal zeta over K over M, and this is 2, and this is omega bar, omega N, this is omega bar. K over M from this definition is omega N squared, so 2 zeta omega N over omega N squared multiplied by omega bar. We can cancel this the square, and omega bar over omega N, what? From here, omega bar over omega N is beta. So this is equal to zeta beta. Move it back to the original term, to zeta beta. So it will replace what term? Which term? It will replace this term. Okay? This part, the root. Okay? No, sorry. It will replace this term. Only this term. So 2 zeta beta all square. Okay? And this term, okay, will replace this root. Okay, so again, F, let's go back, will equal xg times k, okay, multiplied by root 1 plus 2 zeta beta all square. This is the magnitude of what? This is the magnitude of the resultant force coming from omega bar t, coming from xg times k, the stiffness force resulted from the motion of the airs, and the damping force resulted from the motion of the damper. Okay, this is k. What about this angle? Psi. If psi, we can notice that if psi is tan inverse, okay, this term over that term, okay, the opposite over the adjacent, okay, both have xg, we will cancel it together, so it is tan inverse C omega bar over K. But we have already proved that C omega bar over K equal to zeta beta. So psi equal tan inverse to zeta beta. What is the psi? Psi is a phase shift between the resultant force coming from the motion of the earth and the motion of the earth. Okay, because psi is the angle between these two vectors. F is one of them. This is the resultant force of the stiffness and the damping force. And what is this vector? This is the stiffness force that is usually in phase with the motion, and this is the motion of the earth. So psi is the phase shift between the motion of the earth and the resultant force coming from the stiffener and the damper, which is resulted from the motion of the earth. Okay, I think it's clear. This is fine. Okay, so now this is F. Let's put it in or highlight it some like that. Okay, this is F. Okay, and this is the equation of motion. So I'll replace the equation of motion with the amplitude F, and this is psi, and this is omega bar t. So instead of using sine omega bar t and cosine omega bar t, I'll replace it with single force, and it will be sine the large angle, which is psi plus omega bar t. Okay, so to complete our analysis, let's move to another screen. So now we have our equation of motion like that. M x double dot plus C x dot z k x equal, okay, the amplitude of the force, which is xgk root xgk root 1 plus 2 zeta beta all square. This is the amplitude of the red force in this slide, okay? And what angle? The angle, we want the projection of this resultant force on the vertical axis, because when you use the component of this, the two components of this force, you take also the vertical projection on the vertical axis, because you take here sine omega bar t. This is the vertical projection of this part, and here cosine omega bar t, and this is normal to that one. So we all know that the angle, this angle is also omega bar t. Okay, so when you look at this part of this force, 3xg omega bar t cosine omega bar t, also this is the vertical projection of this part. So this is the resultant of these two forces. So taking the vertical projection of this force on the vertical axis is equivalent to take the vertical projections of the components of these two forces. Okay, so now we will write here sine omega bar t, okay, plus what angle? This is omega bar t plus epsilon, okay, and we know the definition of psi from the previous slide. Now, this is the amplitude of the force, and this is a harmonic force, applying the same concept that we have studied together in mechanical vibration. If you have a harmonic force to the right-hand side of the equation of motion, the solution is simply like that. Okay, so I'll repeat the same solution here, but with the terminology of the new forces. This is the amplitude. This is, instead of this F capital, I put this F. Okay, so what will be the motion? What will be x of t? X of t, and we are concentrating on the particular part of the solution, because the homogeneous part will diminish, will dissipate by time. So x particular of t equal the amplitude of the force root 1 plus 2 zeta beta all square divided by k. Okay, this is what we have already derived before. So I divide this with k, so this k will be cancelled. This one, okay. This is f by k divided by root 1 plus 2 zeta beta all square. Sorry, this is 1 minus beta square all square. Just I'm copying this formula, okay? X particular. So this is the amplitude, but take care, we complete this one here, okay? So we complete, there's a missing part, which is completed in this part, okay? This is the missing part of that one, okay? So what's missing? Sine omega power t minus phi. Now my angle is not omega bar t, it is omega bar t plus epsilon. Okay, nothing will happen except that you will respect this epsilon. So it is sine omega bar t plus epsilon, and there will be another phase shift because of the damping in the system. So I'll subtract my phi. Okay, the phi will have the same definition like that we derived before. It will be tan inverse 2 zeta beta over 1 minus beta square. Okay. If you remember, what is the definition of phi? Phi is the phase shift between this x and the applied force. Okay, again, phi is the phase shift between the applied force to the system. This is the new applied or new resultant applied force to our system. And this one is x. This is the motion of the system, which is x. I know implicitly that x is the motion of the mass that I want to isolate from the motion of the earth. Okay, so phi is the phase shift between the force, okay, and the applied force to the system, and x double dot. Okay, now we want to concentrate about this particular term. Okay, this particular term, this is the amplitude of the force. So the amplitude of the force amplitude, okay, or amplitude of the force amplitude, okay, equal what? Equal x g, okay, root 1 plus 2 zeta beta all square divided by root 1 minus beta square all square plus 2 zeta beta all square, okay? This is the amplitude of the force. We can name it as x capital because this is the amplitude of x. So I'll name it as x capital. So x capital over xg equal root 1 plus 2 zeta beta all square divided by root 1 minus beta square all square plus 2 zeta beta all square, right? What is this ratio? This is the ratio between the amplitude of x, which is the motion of the mass, and the amplitude of the ground, which is the motion, the maximum amplitude of the ground. So this ratio, what should it be? Okay, should it be greater than 1 or less than 1? If it is greater than 1, so you are amplifying the motion of the earth. If the amplitude of the motion of the mass itself is greater than the motion or the amplitude of the motion of the earth, so you are amplifying the motion of the earth and transfer it to your mass. Okay, so this ratio should be less than 1. This ratio, what is called transmissibility. Okay, this ratio is, this is the transmissibility. Transmissibility. Okay, this is the part of the motion that will be transmitted from the earth to your system, your mass. Your mass may be a machine in your factory or any instrument that you are supporting on a panel or a board or something like that. So you have to design your suspension system such that this quantity less than 1. So what will we do? We have to plot, to graph this part, okay? How to plot this part, and you have two variables, theta and beta. So in this time, or in this case, we want to fix one parameter and change the other. Usually, we do the following. Okay. This is the x-axis, and this is the y-axis. Usually, we let this one is beta, and that one is the transmissibility itself, which is x over xg. And we fix theta at a certain value, and we plot the curve. What will we plot? We will plot the transmissibility versus the beta. Okay. So you will find the following. You will find something like that. Okay. All the curves will start if you put beta equals 0 here and here, okay, and here. All the curves will, so beta, this term will be cancelled, and this term will be 1, and this term will be cancelled, so it will be 1 over 1. So irrespective of the value of zeta, all the curves will start from 1. So all the curves will start from 1. So you will find something like that. We'll find an amplitude, okay. Then it will decay like that. This is at a certain beta. For another beta, okay, you will find something like that. For another zeta, I'm sorry. Okay, forgive my bad drawing. Okay, you will find something like that. For another zeta, higher zeta, you will find something like that. Okay. I think you noticed that I'm drawing all the curves to pass to certain point here. Okay, all of them are all the curves will cross each other in this particular point. What about this particular point? Let's try to put in this equation beta equal root 2. What will happen? Okay, if you put beta equal root 2 here, root 2, this quantity will be 2. 1 minus 2 will be minus 1. Minus 1 all square, it will be 1. So this will be 1 plus 2 zeta beta all square, and the numerator will be 1 plus 2 zeta beta all square. So the numerator will equal the denominator. So this quantity will be 1 irrespective of the value of zeta. Okay, so irrespective of the value of zeta at beta equal root 2, which is something like 1.4. So this is exactly root 2. All curves will cross each other at this point, and the value of transmissibility will be 1. Another note, okay? Look at this figure. All irrespective of the value of zeta, as we said that zeta is increasing in this direction. So for example, this is zeta 0.1, this is 0.3, this is 0.5, and something like that. So as long as you are increasing zeta, this amplitude will be lower. Okay. So, but all the values before root 2, the values of the transmissibility irrespective zeta will be greater than 1. But after this root 2, all the values of the transmissibility will be less than 1. So what should we do to design a proper suspension system? Okay. So the very obvious notice that you have to have your beta greater than 2 to get a value for the transmissibility less than 1. Otherwise, you are amplifying the motion to your system because the transmissibility here is usually greater than 1 before root 2. After root 2, all the curves is less than 1. Okay. Another note that you notice that the curves are reflecting after root 2, while the blue curve is above the green curve and the green curve is above the yellow curve before root 2. After root 2, this phenomena is reflected. Okay, you know the lower curve here is the upper curve here. The yellow curve was the lowest curve. Here it is the highest curve after root 2. So what should you do according to this note? So after root 2, if you have a large zeta, you will have a greater transmissibility. So after this value, you are requested to lower the zeta as much as you can, because this is the blue curve, for example, has the lowest value of zeta. Okay, this is the second loss. So to design a proper suspension system, the first condition or the first consideration that you have to take into account that the beta or the frequency ratio should be greater than 2. After that, you have to make the zeta lower or low as much as you can. Okay, but you can't make it 0 because you will for a practical system, when you operate your motor or when you are turning your car in. So usually the motors and the vibration system starts from beta equals 0 and go till reaching this quantity. So you will pass through this region, okay, while turning on your motor. So don't make it the zeta. Don't make zeta is 0 because sure you will pass here. So if you have very low zeta, you will have here very high amplitude that may break your system or tear your material or something like that. Okay, this is about the transmissibility of the systems. And as we said that we can call it vibration isolation because we are isolating the vibration of your system from the vibration of the ground. And it may be called also response to base excitation because this is the response of your system, which is this mass, to the vibration or the base excitation, the base on which it is fixed or supported. Okay, thank you very much.